Ooh, I can't wait for my trip to Japan.
Have you ever wondered what makes up a plane?
I've never thought of that.
Let's take a closer look.
So why do materials matter in the aerospace industry? First, let's look at the history of these materials. In the 1900s and 1920s, the Wright brothers created the first airplane using fabric and wood. As commercial and military aviation grew in the 1920s to 30s, materials needed to be more durable, leading to a widespread use of aluminum alloys. During World War II, higher altitude and combat required materials that offered high strength and fatigue resistance. Steel and magnesium were also used to support aluminum shortages during the war. After the war, the emergence of first-gen civil airliners spawned the introduction of titanium. Then came the Cold War. Supersonic aircraft needed heat-resistant materials, pushing titanium and nickel-based superalloys into mainstream aerospace engineering. In the 1970s, structural failures drove stricter certification for fracture and fatigue resistance. Fuel prices also surged, making lightweight structures crucial in the selection of materials. By the 1980s to 1990s, military stealth technology demanded radar-absorbent materials, and commercial aviation focused on reduced costs. This led to a greater use of carbon epoxy composites. Today, there's a greater shift to eco-friendly designs. However, there are still some key requirements for materials that cannot be neglected. They have to withstand high temps, have high strength-to-weight ratio, provide adequate shielding against the elements, and have high corrosion resistance and minimize electromagnetic interference.
Let's now move on to the metals commonly used aluminium and titanium alloys. Both are known for having a high strength-to-weight ratio and good corrosion resistance, which makes them ideal for aircraft and other high-performance structures. Aluminium alloy 707T6 has a lower melting point, so it's easier and cheaper to produce. That's why around 80% of an aircraft's airframe is made from aluminium. Titanium, on the other hand, is much stronger at high temperatures and has a higher melting point, but it's also expensive because it reacts easily with oxygen during production. Now moving on to carbon fiber composites. These materials are incredibly strong and lightweight, and they perform really well under temperature changes. The key is how the fibers are arranged. By layering them in multiple directions, the composite can handle stress from different angles and avoid splitting and delaminating. As shown below, fibers are strongest when stress is applied along their direction, and by combining different orientations, we get a material that is both balanced and durable. That's why carbon fiber is now used not just in aircraft but also in bikes, cars, and even sports equipment. So aluminium is used where cost and weight matter most, while titanium is used in critical parts like engines or load-bearing sections. Of course, each material has its downsides. For titanium, its high oxygen reactivity limits how hot it can actually operate, even though it goes through 1670 degrees Celsius. It starts to degrade around 660 degrees Celsius, and its high cost means it's not practical for large-scale usage. Carbon fiber, meanwhile, can suffer from cracks and delamination, where layers start to separate over time. Once that happens, the structure loses strength. So while these materials are amazing in performance, engineers are always wondering how to balance cost, strength, and durability depending on application. Now let's move on to aircraft tire. Material scientists must create a composite that handles 800,000 pounds of impact and swings from negative 40 degrees Celsius to 200 degrees Celsius. The solution is a mastery of nylon or steel cords and polymer chemistry. The future is about smart tire systems and sustainable bio-based rubber to maintain performance while being responsible. Next, the turbine blade. This is an infernal 1200 degrees Celsius heat and 10,000 times gravity of centrifugal force. The material secret is nickel-based superalloys grown as single crystal structures to eliminate weak points. Our research is advancing to ceramic matrix composites for 1300 degrees Celsius plus operation and using additive manufacturing to 3D print complex cooling channels inside the metal itself. So materials play a crucial role in shaping the performance, safety, and efficiency of aerospace technologies. Through our research, we have seen how advanced materials like titanium alloys are carefully selected for strength-to-weight ratio, heat resistance, and durability under extreme conditions. As material science continues to evolve, innovations in nanomaterials and sustainable composites will further revolutionize aerospace design, paving the way for lighter, stronger, and more energy-efficient aircraft in the future.